in differential calculus. Till now we have learnt about limits, theorems on limits and its applications. Today we are going to learn one more interesting concept, and it is continuity. What is continuity? In general, we define continuity as it's a process. It's a process that doesn't stop. It's a process that's keep on happening without any great changes. Yes, continuity is a fact that something continues to happen or exist, continues to exist with no great changes or interruptions. For example, the flow of water in a river, and also the flow of time in our life, that is your age, as it is continuously moving. Look at the functions, the graphical representation of few functions. So, the curves or the arcs we are representing for the function is flawless and it is keep on moving. So, we can call these functions or continuous functions. It doesn't have any interruptions. Look at these functions. These functions, these graphical representation of functions are few examples for discontinuities. So, we can define continuity as it is, let's take an open interval I, and f is a function from I to R is real number line. Then f is said to be continuous at x naught, at this point x naught, if it is defined in a neighborhood of this point and if the limit of this function as the independent variable x tends to x naught exists and it is equal to the value of the function x is equal to x naught. In simple words, we can define continuity at the point x is equal to x naught. So, first point, it should be defined in a neighborhood of x naught. F of x naught should exist, and also limit x tends to x naught, f of x also exists, and then finally limit x tends to x naught, f of x should be equal to f of x naught. If the function satisfies these three conditions for a particular point x is equal to x naught, then we can define these functions are continuous functions. Let's see a few examples of continuous functions first. Constant function is continuous. If it is a constant function, it is always continuous at each point of R. Similarly, power functions, let f of x is equal to x power n, then it is also continuous in the domain R, that is minus infinity to infinity. In the real number line, it is always continuous, the power function. Polynomial functions are also continuous. Quotient functions or rational functions are also continuous, but with a particular condition that the denominator should not be equal to 0. So, here q of x is the denominator and q of x should not be equal to 0. It is a basic property of rational function also. Okay. So, polynomial functions, the rational functions are also continuous with the particular condition that its denominator should not be equal to 0. And the trigonometrical functions, the circular functions in sin x and cos x are also continuous. Okay. In the real number line, minus infinity to infinity, limit x tends to x naught, sin x is equal to sin x naught. Similarly, limit x tends to x naught, cos x is equal to cos x naught. As a consequence, tan x, cot x, cosecant x, secant x are also continuous on their proper domains in view of the reciprocal and quotient rules in the algebra of limits. You mean tan x, we used to denote tan x as sin x by cos x. So, it is a rational function, isn't it? Tan x is equal to sin x by cos x, and it is a rational function, and the denominator should not be equal to 0. That is only mentioned here. Similarly, for cot x, it is cos x by sin x. In that case, sin x should not be equal to 0. The nth root functions f of x is equal to x bar 1 by n are continuous in their proper domain. The reciprocal function is also continuous, and the denominator should not be equal to 0. So, it is continuous at the point or difference 0. Okay. So, here x is in the denominator and it should not be equal to 0. So, all the other values except 0, it is continuous in all the other values. Here the function, it is an example for continuous functions. So, the greatest integer function is not continuous at x is equal to 0. X is equal to, in this particular point alone, it is not continuous. And the modulus function, we used to define modulus function as mod x is equal to minus x if x is less than 0, and 0 if x is equal to 0, and x if it is greater than 0, and it is continuous in all the points. Similarly, the exponential function is continuous, the logarithmic function is also continuous. If I have two functions f and g which are continuous at some point x naught, then their sum, that is f plus g, is also continuous at the same point. F minus g is also continuous at x is equal to x naught, and their product f into g is also continuous at x is equal to x naught. F by g is also continuous at x is equal to x naught, with the condition g of x should not be equal to 0 as it is in the denominator. Composite functions theorem on continuity. If f is continuous at g of x naught and g is continuous at x naught, then we can tell f composite g is also continuous at x naught. Continuity in a closed interval. Let us take a closed interval a comma b, and f is a function from closed interval a comma b to r, and it is said to be continuous on the closed interval a comma b if it is continuous in the open interval a comma b, and limit x tends to a plus f of x is equal to f of a, and limit x tends to b minus f of x is equal to f of b. So, if the function is said to be continuous, then it is continuous on the open interval a comma b, and it should satisfy this condition also. That is, the function is continuous from the right or at a and continuous from the left at b, and it is continuous at each point x naught that belongs to the open interval a comma b. First, let us solve few problems. Prove that f of x is equal to 2x square plus 3x minus 5 is continuous at all points in R. F of x naught is, instead of x, they have substitute x naught. So, 2x naught square plus 3x naught minus 5. Let us calculate what is limit x tends to x naught f of x. So, limit x tends to x naught, 2x square plus 3x minus 5. So, limit, we can apply limit to all the three terms, and as x tends to x naught, here x will become x naught. So, 2x naught square plus 3x naught minus 5. From equations 1 and 2, limit x tends to x naught f of x is equal to f of x naught. So, f of x is continuous at all points of R. In other words, we can solve the question like this also. Here f of x is equal to 2x square plus 3x minus 5 and it is a polynomial function. We studied that the polynomial function is continuous at all the points. So, here f of x is a polynomial function and so it is continuous. We can conclude like this also. Examine the continuity of the following. First problem, x plus sin x. So, x is continuous at all the points in R and sin x is also continuous in all the points of x belongs to R. So, x plus sin x is also continuous at all the points x belongs to R. Here similarly, x square cos x. So, x square is continuous and cos x is also continuous. So, x square cos x is also continuous in all the points x belongs to R. Let us check the continuity of few more problems. F of x is equal to e power x tan x. E power x tan x. E is the exponential function. So, exponential functions are continuous. So, e power x is continuous. In the property in the examples we have learnt. So, e power x is continuous. What about tan x? Tan x is also continuous except x is equal to 2n plus 1 pi by 2. Because for tan x, we have tan x as sin x by cos x. So, cos x at what points cos x will become 0, we have to exclude that. So, x is equal to 2n plus 1 into pi by 2. At this point, cos x will become 0, cos theta will become 0 at this point. So, we are excluding that x belongs to R minus 2n plus 1 pi by 2. So, before that cos value, when cos value will become 0, for example, cos 90 is 0, isn't it? Yes. So, if I give n is as n is belongs to z, if I give n 0 for n, this will become pi by 2, x will become pi by 2. So, in the denominator cos pi by 2 will become 0. So, I am excluding that. Similarly, if you can substitute any points and you will get 0 in the denominator and so we are excluding 2n plus 1 pi by 2 from the real number line. Okay. So, 7th one, f of x is equal to x square minus 16 divided by x plus 4. X square minus 16 it is a polynomial function and it is continuous. X plus 4 is also continuous. But in the denominator x plus 4 in the denominator, so in some particular point it is not continuous. So, if you equate the denominator, you can find the point x plus 4 is equal to 0, the denominator is equal to 0. So, x is equal to minus 4. So, f of x is continuous for all except or difference minus 4. X is equal to minus 4. In this point, it will become 0, the denominator will become 0. So, we have to exclude, we have to ignore. So, it is continuous for all except or difference minus 4. Find the points of discontinuity of the function f where f of x is equal to 4x plus 5 if x less than or equal to 3 and 4x minus 5 if x is greater than 3. So, f of x, it is, so we have to find the value at 3. Okay. So, first let us calculate the left hand limit, that is 3 minus, and then we will calculate the right hand limit 3 plus. So, limit x tends to 3 minus f of x. 3 minus, that means less than 3. So, which function? 4x plus 5. So, 4x plus 5, instead of x we can substitute 3. So, it is 17. Next, limit x tends to 3 plus f of x. 3 plus means the right hand side of 3. So, it is x greater than 3. So, 4x minus 5. So, 4x minus 5, in this instead of x we have to substitute 3. So, it is 7. Here the left hand side limit and the right hand side limit are not equal. Not equal. It should be equal for continuous functions. Left hand side limit and right hand side limit should be equal. But here it is not equal. So, at this point 3, the function f of x is discontinuous. So, f of x is discontinuous at x is equal to 3. For what value of alpha is the function f of x, x power 4 minus 1 by x minus 1, if x is not equal to 1, and alpha if x is equal to 1, continuous at x is equal to 1. For which value of alpha this function is continuous, we have to find. So, limit x tends to 1 f of x. Limit x tends to 1 x power 4 minus 1 divided by x minus 1. Okay. So, x power 4 minus 1, we can write it as x power 4 minus 1 power 4. Appo a square minus b square is equal to a plus b, a minus b. So, here we can write it as limit x tends to 1 x square minus 1 into x square plus 1 divided by x minus 1. So, this x square minus 1 can be written as x minus 1 into x plus 1. So, into x square plus 1 divided by x minus 1. We can simplify this. Limit x tends to 1 x plus 1 into x square plus 1. Now, we can substitute 1. So, 1 plus 1 it is 2 and 1 square plus 1 it is also 2. 2 2's are 4. So, when limit x tends to 1, f of x is equal to 4. So, f of x is continuous at x is equal to 1 and the alpha value is 4.